Section 7.8, Powers of I. In the following discussion, we'll show why there's no need to use powers of I other than 1 when writing answers. So we're going to do some simplifying. We already have seen problems by definition where I squared is equal to -1. And using that, if they're asking us to simplify I to the third and our exponential rules, I to the third is equivalent to I to the second times I. Since I to the second is -1, we can replace that. Simplifying this further, -1 times I is I. I to the fourth, similarly, we can break this down into I to the second times I to the second. I to the second, by definition, is -1. Likewise, we have another -1. -1 times -1 is +1. Now, we can either continue breaking higher powers down into I to the second, or if you see this pattern, I to the fourth being a 1, we can use that and simplify further because of the fact that there is a cycle between I to the first through I to the fourth, looking at the following. I to the fifth, since we just saw that I to the fourth is equal to 1, it would be to our advantage to break this down into I to the fourth times I. Why? I to the fourth we just found was a 1. 1 times I is I for our final answer. We could have, if we just relied on I to the second power with its definition equal to a -1, we could have taken I to the fifth and broken it down into I to the second times I to the second times I. Common bases multiplied together at our exponents. We have our I to the fifth power. I to the second power is a -1. We have another -1, and we have our I. Negative times negative, 1 times 1 gives us a +1 times I, or I. It's kind of up to you. Again, it's handy, particularly since we've just defined I to the fourth equal to 1, to use that fact. Let's look at a couple other examples and strategies we can use to simplify this. We have a product raised to a power, which means each of those factors is raised to that power. Well, 2 to the sixth, if you multiply that all out, turns out to be a 64. I to the sixth, using I to the fourth is equal to 1, can be broken down into I to the fourth times I to the second power. Common bases, add your exponents, would be back to the equivalent I to the sixth. I to the fourth, though, we know is 1. I to the second power is a -1, and we're multiplying that by 64. 64 times 1 times -1 results in a -64 for our final answer. I to the 27th. How many powers of 4 go into 27 evenly? Well, 27 divided by 4 would be 6 of them, with 3 left over. So writing it as a power of I to the fourth, we'd have to raise that to the sixth. That would mean we have I to the 4 times 6, or 24th power, but we have an I to the 27th, which means we also need an I to the third. Just to verify this, power raised to a power, you multiply your exponents, that's the 24th power. Common bases, add your exponents, 24 plus 3 would bring us to the 27th. I to the fourth by definition is 1. 1 to the sixth power is 1. I to the third, if you recall what it's equivalent to, and if not, as long as you know I squared, we can always simplify these. I to the third is an I to the second times an I to the first. I to the second, we've already simplified this to a 1. I to the second is a -1 times our I, leaves us with a -I for our final answer. In this last example, we're adding, they aren't like terms. We'll leave the I first term alone. I to the third we just saw in the last example breaks down into an I squared times I. I squared is a negative 1 times I would make it a negative I, as we had in the previous one. And then we now have common terms. 1 positive I plus a negative 1 positive I are additive inverses, canceling out, giving us a value of 0.